All right, so I'm going to walk through some, probably not all, of the questions from our first test. One thing to note is that right on here, the second bullet just says you'll be graded on your answer and your work and justification, right? And I mentioned that numerous times in class. I mentioned it before I gave you the test as well. So that was one area that kind of hurt some folks. There were also some suggestions as far as strategies and things like that. So if you felt you were a little short on time, maybe take a look at those. All right. So the very first one, this should have looked awfully familiar. A lot of these should have looked familiar. Many of the problems came as versions of what you saw in the test review or things from the notes. So this idea, what makes this continuous? Well, the idea is, for all values not equal to -3, we're going to use that first function. So really, what are we trying to do? We're trying to find the limit as t goes to 3. Oh, sorry, -3. My bad. -3 of t squared minus 9 over t plus 3. So this thing, we should be able to square, or factor the square rather. So t minus 3, t plus 3. So this is where factoring, having that down, sorry, I said 3 and I wrote 9. Having that down is really important, recognizing that the difference of squares and that you can factor it really easily. So we go, okay, cool, t plus 3 is going to get knocked out of there. And that was really the issue with plugging in -3. So now we're left with a limit as t goes to -3 of t minus 3. And if you want to keep the parentheses around, that's fine. You don't need them, but you can have them to make it a little more clear. And then we plug this in. We say, okay, if t is -3 and we subtract 3, I guess my answer is going to be -6. And that's what A was supposed to be. So A was supposed to be -6. This graph would basically have a hole in it, and this value would fill in that hole. All of this is pretty clear work, right? We're including the fact that, hey, I recognize it's a limit. We're showing our factoring. We're keeping that limit around until we actually plug in the value, right? At the step right over here, we remove the limit because we have actually plugged in -3. We've applied the limit. All right. In number 2, using the graph to evaluate the limits. Well, this one, most people did pretty well with, just in terms of, a lot of times having the visual is not too bad. So as x goes to 3, what's our function doing? Well, since it's continuous at that point, all we really need to do is say, well, what's the y value? Okay, that's 2. As x goes to 2 from the left, well, yeah, coming from the left versus from the right, turns out those are going to the same place. So from the left, I'm going to 1. And since they go to the same place from the left and the right, then the overall limit, which is part C, is also 1. However, as we approach 5, so the next questions are about 5. As we approach 5 from the left versus from the right, those are going to go to different places. So 5 from the right, that's going to be +3. But from the left, we're trying to go to 1. Right? Keep in mind, we don't get there, and that's okay. Limits don't care, right? Limits are like, where are you trying to go? And then the limit as x goes to 5, well, this thing doesn't exist because the two pieces above it, right, from the left and from the right, don't agree. So that doesn't exist. All right, and then we have what happens as x goes to infinity or as x goes to -infinity? Well, we notice that we have, as we go to infinity, this is just a constant function here, right? This is going to keep going. So it's just going to be 3. And then -infinity, well, okay, if I head out this way, right, it's just going to keep going, keep going, keep going, right? It appears, we assume that the behavior continues in the same fashion, like there's not some major turnaround, otherwise that would have been part of the graph. So this thing's headed to -infinity. Now, we talked about limits involving infinity, -infinity. Yes, those we originally said don't exist. Technically, there is not a limit, but we want to distinguish between limits that actually have a pattern or a direction versus ones where the two sides don't agree. So this one we should be saying -infinity. All right. These guys, yeah, this kind of emphasizes the same point. So 1 over x looks like this. As we go to 0 from the left and from the right, those two sides don't agree, so this does not exist. However, 1 over x squared makes this positive. So they agree. This limit's going to go to infinity, so this is false. That limit does exist. And then, lastly, this piece is false, and it's probably because we forgot about maybe applying one very important piece of this. So we can take the leading terms for both. So the leading terms, meaning the terms with the highest degree, are negative x cubed and positive 16x squared. If you simplify this thing, or if you just noted, hey, the degree on the top is greater than the degree on the bottom, this thing is going to go to infinity, but there's a negative there. So this is actually going to go to negative infinity. So we got to be careful about that, that negative. That'll get you. Okay, slope of the secant line. Remember, the secant line is basically just between 2 points. So we have some kind of function that's a parabola, right? 2x squared minus 4x. And we're looking at 2 different points on there. I'm just choosing, kind of a visual like this, and basically saying, okay, if I connected those points, what would the slope of the line be that connects those points? That's the secant line. I'm not going to go through that one. You can do that one on your own. Then we want to use the same function and basically figure out, right? This thing is almost the definition of the derivative, but not quite. Right? It's the definition without the limit. And hey, look at that. We're going to need to find the slope of the tangent line, aka the derivative, right? So down here is when we're going to apply the limit portion of this and let h go to 0, right? The denominator is going to go to 0 of whatever we found up here, right? We just had to figure out which one that was. So that piece, we had to be kind of mindful as we went through and say, okay, f of x plus h, right, which is the first term we need, that's going to look like 2 times x plus h squared minus 4 times x plus h, right? So then we expand this and we're going to get x squared plus 2xh plus h squared. And one thing that we notice is that really being mindful with your algebra is very important, right? Distribute the negative, so negative 4, negative x. We're distributing the 2. So we get this going on, right? So then when I do the next thing, which is, right, subtract from this f of x, I'm not going to show you all of the steps, but basically what would happen is we'd have a couple terms that end up canceling out. So 2x squared from f of x plus h cancels with 2x squared here. Negative 4x ends up canceling with this negative 4x again because we're subtracting f of x. So we end up with 4xh plus 2h squared minus 4h. And you can factor out an h, right? All terms have an h. So we can say, okay, 4x plus 2h, there should still be 1 there because we have h squared minus 4. So when we put this all together, when we do f of x plus h minus f of x all over h, right? It's this divided by h. Well, we end up canceling out the h's. We end up with something that's pretty straightforward like this. So I'm not showing every step here, but I'm kind of giving you a sense of like, hey, you should be walking me through this, right? Showing me the work that we need. So we get 4x plus 2h minus 4. So that is this guy, right? So that would be what we filled in. All right, once we have that, to find the slope of the tangent line, well, f prime of x is the limit of this difference quotient we just found. So it's the limit as h goes to 0 of 4x plus 2h minus 4. So we just plug in 0 for h, and what we get is 4x minus 4. But that's the general derivative. If I want to know the derivative specifically when x is 3, I just plug that in. And we're done. Slope is 8, right? This thing, if I just simplify it, slope is 8. Finding the equation of the tangent line, right? This just, I kind of told us exactly what we need to have. mx plus b. Well, guess what? Your slope m is going to be 8. We got that from up here. So really, you just need to figure out what is f of 3 so that you have the point, right? X comma y. And then you can plug those in, solve for b, etc. All right, limits. First rule of limits, just plug it in. So part A here in number 5, we just plug this in. 2 times 2 plus 4, that's fine. 2 squared minus 4 times 2 minus 12. This is fine as well. So we get 8 on top. And on the bottom we get 4 minus 8. So negative 4 minus 12. So this is negative 16. If you want to call this negative 1/2, that's fine. If you called it negative 0.5, it was very clear that we probably just used our calculators or something like that. Your calculators are there as an extra tool, but we still have to justify, right? Justify your answers clearly. That's what the directions say. That's what I've been saying repeatedly. So if you didn't do that, you should be kicking yourself a little bit because I've been emphasizing that over and over and over again. Okay, in part B, if we plug it in, we're going to run into some issues. So what happened in B? Well, we were supposed to, again, not make a table for these. If there's another method, then use it. So this is factor out of 2. We get x minus 2. And then factor the bottom, we get an x minus 2 and an x plus 6. And so we should have seen these two cancel. And then we get to a place where we can apply the limit, yada, yada. We can keep going from there. So we end up getting, at the end of the day, either 2/8 or 1/4. Okay, you should show that stuff. I'm just saying. I'm kind of talking through it. Okay. The next part of this, right, we have limits going to positive or negative infinity. Well, this is a time when we can use those leading coefficients again, right? This is going to look like the limit as x goes to negative infinity of x cubed over, let's see, I was drawing, so I don't know if that, yeah, okay, it's a plus, over positive 3x to the 5th. Right, the bottom power, a lot of you did like an m versus n situation, powers of the top versus powers of the bottom. So here, right, the power in the bottom is greater, so this thing should go to 0. You can also simplify this. So you can say, okay, if it looks like this, which we can only do if we have x going to positive or negative infinity. But if that is the case, then really we're looking at 1 over 3x squared, right? You can cancel x cubed in both places. And then it's a lot more clear why this thing goes to 0, because the top is 1 and the bottom keeps getting bigger. Cool. All right, similar thing in D. So I put these huge numbers in there as a distraction, but really what are the terms of importance? 4x to the 4th, 6x to the 4th, when those powers are the same. Right, when those degrees are the same, you just take the ratio of the coefficients, 4 over 6, or 2/3. You can, again, justify it like above, or you can say, hey, m equals n, so we use the ratio, whatever. There's a lot of ways to note that. There wasn't a ton of work that you needed to show here, but you had to do something. You had to circle these guys, tell me m is equal to n, something. All right, in part E, there's a couple ways to do this. This is probably a case when you want to use a table. Most likely, but I'm going to show you a way that you didn't need to use a table, or at least you could kind of work your way through it. So 2x plus 5, and if I break this up into x minus 3x plus 3, I know that x plus 3 is fine. So I could leave that x minus 3 off to the side. So I could solve for this thing. I could split the limit up, solve for this, and then separately solve for this. So I could say, okay, well, this is really two limits. Going to 3 from the right, I have 2x plus 5 over x plus 3 times the limit of, well, x goes to 3 from the right still, 1 over x minus 3. And this graph looks a lot like 1 over x. So anyway, we could do this and kind of work our way through to figure out what's going on, or we could use a table. So there's a number of different ways to do that. Lastly, this guy, we need the fact that the limit of sine x over x, if we let x go to 0, is 1. We did this one in one of the videos, and in class we used it a bunch. So all I really need to do is take the 1/4 out. Right, constant multipliers can come out front. So this is 1/4, not 4, because it's in the denominator. So guess what? If this thing goes to 1, then here's 1/4. Right, so that's that.